In this lecture, we will be discussing optimization fundamentals. So the focus here is for nonlinear optimization, and we need a few results from analysis to be able to talk about this stuff. And the first one is the concept of an open set. So we're working in Rn, so n-dimensional space. A subset F contained in Rn is open if for every x in F, so every n vector of real entries, there exists an epsilon greater than 0 such that the ball of radius epsilon is contained in F. Mathematically, that's the set of vectors, y and Rn, such that the norm of the difference of y and x is less than epsilon. That set lies within F. Okay, so that may feel like a lot, but if we break this down with a picture, it's more straightforward to understand. So think about when you first learn calculus and you learn about the idea of an open interval. And when you learn about an open interval, you think, okay, that's an interval that just does not contain its endpoints. And we are generalizing that here a little bit. And think about how this open interval satisfies this definition as an open set. So pick an x inside the set. Well, you can find a ball, in this case, just pick your epsilon, say to be that size there. A ball of radius epsilon, in this case is this little interval, is completely inside the set. And you can do this for any x in this open interval. So if you pick an x very close to, say, this right endpoint, you can pick your epsilon to be half the distance between that x and this endpoint, and you can get a little interval with x at the center inside of the set. And that's what it means for this interval to be open. And now we can just think of this as a more general version of that, except in higher dimensional space. So the way you're thinking of it now is you have a set. Let's draw it like this. You're in n-dimensional space, and we say, okay, what does it mean for it to be open? Well, if you pick a vector x in that set, you can find some epsilon, and think of it as the radius of a ball, such that if you form that ball of radius epsilon centered at x, it is completely contained inside the set. That's what this says. To sync up with this formal definition, this is saying if you pick all the vectors y such that, so think of this as your y here. Well, what is this norm of y minus x? If you think in terms of Euclidean distance, so think of this as the 2 norm, that would be the Euclidean distance between y and x in n-dimensional space. That's going to be the length of this line segment. And so this set notation here is saying all the vectors y that are within a distance of epsilon of x. So that would be all the y, all the possible orange points inside this ball, collectively making up that ball. Okay? That ball is inside our set F. And that's what it means for it to be open. And you can see if you pick any x, you're going to be able to sneak that ball in there. Just find the minimum distance to the boundary and choose epsilon to be, say, half of that distance, and you can put a ball around your x point that stays inside the set. So that's what it means for a set to be open formally. Another way you can think of it, in Rn, it's a set that does not contain its boundary. So if you pick a point on the boundary, the way we define a boundary point, by the way, is any ball that you put around your boundary point. contains points in the set and also points not in the set. And we can think of an open set in Rn as a set that contains none of its boundary points. So that's a nice intuitive way to think of this. But this is our formal definition. Now that we have the definition of an open set, we also need to define neighborhood. This is something we use when we want to just put an open set around a point. So a neighborhood of a point x in Rn is an open set that contains x. Any open set that contains x. And we'll see that show up in a lot of our definitions in optimization. Another concept that we need is that of continuity. So let's remind ourselves what a continuous function looks like in single variable calculus. So a function from the real numbers to the real numbers is continuous at the point A if for every epsilon greater than 0 there exists a corresponding delta greater than 0 such that the absolute value of f of x minus f of a is smaller than epsilon whenever the absolute value of x minus a is less than delta. Okay, this is another definition that feels complicated and is much less so when we draw a picture. So I want us to just think of kind of a typical graph for a continuous function. And when we think continuous functions of single variable, that means no jumps, no holes, and no vertical asymptotes. And so we want to think of what it means to be continuous at the point A. Well, the idea is to think of this epsilon as given. So someone gives us this epsilon, which is some small number greater than 0, and we want to think about what's happening near x equals a. And so the way we're going to set this up is to make a band of radius epsilon centered here on the y-axis at f of a. So this line up here would be the line y equals f of a plus epsilon, and this line here, y equals f of a minus epsilon. And what this definition says is, can we get the blue curve to be inside this band? And the definition of continuity says the function is continuous if, when someone puts up this gray band, in other words, they're giving you this epsilon, we can find this delta greater than 0, such that we're inside the gray band whenever the absolute value of x minus a is less than delta. So think of this absolute value of x minus a as the distance down here on the x-axis between points x and this fixed value a. And what we see is, we'll do it in lavender, if we were to say pick this interval, and this interval is going to have radius delta. So that's our delta greater than 0. And if we pick values for x inside that interval, let's put up our vertical band now, then we will get our curve inside this box. And so that's the key, is the idea of getting the blue curve completely in this side, in this box. So anytime we're given this epsilon greater than 0, we are asked, can we get the curve within this horizontal gray band? And our answer is, if we can find this vertical lavender band such that the blue curve is inside the box in the intersection of the two, then that's what it means for f to be continuous at a. And it's important to remember this works for any epsilon greater than 0. So if we are given a smaller epsilon and you shrink the width of this gray band, and then we only need to shrink the width of this lavender band and we get the blue curve inside that box, if we can always do that, if we can always answer the gray with the lavender, that's what it means for f to be continuous at x equals a. We now want to look at the definition of continuity for a function of n variables. So when we're dealing with optimization, we are usually looking at these types of functions that take in an n vector and then spit out a number. The lingo is usually your n vector are your decision variables, and then you spit out a number like cost, for instance, and you're, say, trying to minimize cost. So we want to think about functions like that, and we want to think about what it means for such a function to be continuous at a point A in Rn. And here is our definition, and it's very similar. For every epsilon greater than 0, there exists a delta greater than 0 such that the distance on the z-axis, we're going to do this in 3D just to try and understand it here, between f of x and f of a is less than epsilon whenever the distance down here in the domain, in the plane, is less than delta. So I want us to think of this kind of example where we have a function of two variables, z equals f of x1, x2, and so our domain is down here in the plane. And we will have our function value f of a here on the z-axis. So I want us to think of this being a point on the surface, z equals f of x1, x2. I'm not going to draw the surface because it kind of muddles the picture. But here's how we want to think of this. Again, someone gives us an epsilon. And now we're going to think of, on the z-axis, f of a plus epsilon here, and f of a minus epsilon here. Now the difference is these, we want to think of these as planes. So we have an upper plane here, and then a lower plane defined by z equals f of a minus epsilon. The upper plane would be z equals f of a plus epsilon. And so what this is saying now, this condition here, the absolute value of f of x minus f of a being less than epsilon, is saying we want to pick points x such that if we plug them into f, the value of f is going to be within, now we have this slice, like a slice of bread. So the surface should be inside this slice, in between these two planes. And our function is going to be continuous, so the same kind of idea, if we can find a delta such that any x that is within a distance of delta of a, remember that's what this means, and we can draw that down here as a disk of radius delta. So any x that falls within that distance delta of a down here in the domain gets us the function inside of this slice of bread. So if we put this up here, we can now think of it like a hockey puck. So if we pick any point down here in this lavender shaded region in the domain and we plug it into the function, it's going to be inside this hockey puck. So that's the intersection of the region above this disk and this region between the two planes. And the idea holds for any epsilon greater than 0. So if someone gives us a smaller epsilon, then this slice of bread gets thinner, and we just need to tighten up this disk here with a smaller delta. If we can always answer that epsilon with a delta, that gets us this hockey puck, such that for any x that we pick down here in the shaded region, when we come up here, the surface, the point f of x is going to be inside this hockey puck. That will mean that f is continuous by definition at x equals a. When you don't have continuity, discontinuities can be more complicated for a function of more than one variable. But when you think of what you had with a function of one variable, your function is continuous if you don't have jumps, you don't have holes, you don't have vertical asymptotes. It's kind of a well-behavedness of the function. It's a similar kind of thing here. Your function lacks a lot of that weird type of behavior if it's continuous. Now that we have these two concepts, open set, continuous function, we can now start to talk a little bit more about optimization. For our remaining definitions and results in this lecture, we will make the following assumptions. So first, our function that goes from Rn to R is twice continuously differentiable. So that means it has all second-order partial derivatives, each of which is a continuous function. And this is the notation that we use for that. So we read this as f as an element of the space of functions that have all second-order partial derivatives being continuous, and this is its domain, Rn. We're going to assume that we're doing unconstrained optimization, so we have no constraints on our x. Our domain is just n-dimensional real space, and our goal is to minimize f of x over the domain Rn. And it's worth noting that you may think, well, I want to maximize my function. Well, if your goal is to maximize, say, f of x, well, you can just rewrite that as minimizing negative f of x. And in nonlinear optimization, we tend to focus on minimization problems because when you start to get into the second order conditions, you're dealing with this positive definiteness idea of the second derivative information, which is a little bit nicer than what you deal with if you maximize your objective. So we tend to focus on minimization. Our first definition is that of a global minimizer. So we say a point x star in Rn, and we usually write a star as a superscript for a minimizer, is a global minimizer if our function has some global minimizer, x star, well, that's the point in the domain where the function achieves its lowest possible value. So if you plug in any other x value from the domain, you should get something greater than or equal to what you would get if you plugged in this x star. And that gives us the definition. So f of this x star is going to be less than or equal to f of x for any other x in the domain. And we see that's what we have here. So our x star is a global minimizer if f of x star is less than or equal to f of x for all x in Rn. That's generally our goal in optimization, is to find a global minimizer. But of course, we have to be careful because we also have the issue of a local minimizer. So a point x star in Rn is a local minimizer if, now we want to think of the kind of case where you might have a function that, say, has more than one local minima. And so, maybe here, this is the global minimizer. But over here, we have a local minimizer. And a local minimizer is going to be an x value where certainly this is not true, because we could pick an x, say, over here, and we would get a value for the function that lies below this. What we want instead is some neighborhood for x star. And restricted to this neighborhood, the function is a minimum. And so we define local minimizer if f of x star is going to be less than or equal to f of x as long as we choose x from this neighborhood, which we call n. And so that gives us the definition for a local minimizer. So if there exists such a neighborhood, n, of x star, such that we have that minimum condition, f of x star is less than or equal to f of x for any x chosen from that neighborhood. And it's worth thinking about this just for a moment as we're getting into the fundamentals of nonlinear optimization. One of the challenges in nonlinear optimization is not getting caught in a local minimum that is also not a global minimum. Now, of course, we're drawing this picture here with a function of one variable, but if you have a function of 1,000 variables, you can't draw it. And so you wouldn't necessarily be able to see that, we found this local minimizer. But look, there's a better one over here. There's a global minimizer over here. So that's something that we are generally aware of when we're doing nonlinear optimization. Now, we also expand the definition of our local minimizer a little bit more to weak and strict or strong. And all that this does for a weak local minimizer is we allow the inequality to happen as a less than or equal to inequality. A strict or a strong local minimizer, we have a strict inequality. And then you have to, of course, outlaw the point x star itself. We can illustrate the strong case. Here, maybe we have this x star, and we see we can find a neighborhood around it such that when we restrict to that neighborhood, any x that we pick, when we plug it into the function, we are going to get a value for the function that is strictly larger than what we would get here at x star. For the weak local minimizer case, you could have something that looks more like this for your function, where maybe we level off. And now you could pick this x star, and we look up here. Now it is going to be less than or equal to any other value that we pick in this lavender interval when we plug it into the function, but you will get equality. This is meant to be drawn so that this is kind of a flat spot. So when you have a weak local minimizer, you can think of it where you can get this kind of flat spot. With a strong local minimizer, you wouldn't get that. Let's do a couple examples. One very basic example for a function of a single variable, f of x equals 1. We know that this is just a horizontal line of y equals 1. And the question is, what are the minimizers of f? It's a very basic example, but think about just picking any point. Well, you know that f of that x value equals 1. That's true for any x value. Maybe we could say that over here was, say, x2. Why don't we say x1 and x2? F of x1 is 1. F of x2 is 1. Well, that means f of x1 is less than or equal to f of x2 for all x1 and x2. Okay, so that means every x1 is a local minimizer. A weak local minimizer, but a local minimizer. So all the points in the domain are local minimizers and also global minimizers of f, because you can't get lower than 1. Another example, g of x equals x minus 1 squared. Well, we can look at this and kind of guess what the global minimizer is, because you know if you take any expression and square it, you get something greater than or equal to 0. So the smallest this can be is when what's inside the square here gives us a 0. And so that's going to give us x equals 1. And of course we know that the graph of this, y equals x squared, shifted over 1 unit, and so we know we get something parabolic like this, and we know that its minimum, global minimum, happens here at x equals 1. So x equals 1 would be the global minimizer, and it's also a strong local minimizer. How about if we go to a function of two variables? Well, using the same kind of logic here, if we have f of x1, x2 is x1 minus 1 quantity squared plus x2 minus 2 quantity to the fourth, well, these are both even powers. And so we know that, like before, the output of this function is always greater than or equal to 0. So we know its global minimum will happen to be 0 if we can get both of these two terms to be 0. And we know that that's going to happen at the point 1, 2. And so that would be our global minimizer in this case. And we also know that this is a strong local minimizer. There's no flat spot there. So this is going to be a paraboloid, which we will graph using software on the next page. But if you think of it like this, so we want to graph the function z equals f of x1, x2, and we know that down here at the point 1, 2 in the domain, we have this x star. And one way that you can think of this is slicing through the surface. So if you were to slice through the surface with, say, the plane x1 equals 1, Right? So think of that as the plane parallel to the x2 z plane. When x1 is fixed at 1, that knocks out this term, and you're left with z equals x2 minus 2 to the 4th. And so that's going to be this upward opening parabola for that slice. And then if you slice through with the plane x2 equals 2, so now think of the plane that's parallel to the x1z plane here at 2. x2 equals 2 knocks out this term, and you would get z equals x1 minus 1 quantity squared, which we know is also this upward opening parabola. And so you would get this paraboloid opening this way. And we'll see it graphed better actually using GeoGebra on this next page. And you can see down here, so this is the x1 axis here. Here's the x2 axis, and you can see that this lowest point here, that is happening at x1 equals 1, x2 equals 2. Things can get a little bit more interesting than these, I would say, more trivial examples that we just worked on. What about if we have x1 not appearing in the function? So f of x1, x2 is x2 minus 1 squared. So this is kind of interesting. Let's just think about what it looks like if we do not consider x1 at all. And so let's think about these x2z plane. Well, like before, we know that this is a parabola. We should have this kind of global minimizer happening when x2 is equal to 1. But what about x1? I mean, again, we know that this is greater than or equal to 0. So the smallest this function can be is 0. And we see that we achieve that with x2 is 1. But x1 could be anything. And we still achieve that global minimum of 0. So now let's try to think with an extra dimension. Throw in your x1 axis here. And what you do now is you draw this parabola out in the direction of x1. And what happens, and this is a little bit more challenging to draw, is you get something that looks more like a parabolic half pipe. So when I say half pipe, think like skateboarding or snowboarding. So now you have this half pipe here. And what's the lowest part of the half pipe? Well, you have a whole line down the base here with a z value of 0 as long as your x1 value is 1. Drawn better? On the next page here, this is what that parabolic half pipe looks like. And what we want to think about now is characterizing that set of global minima. And we know it's this whole ridge that runs along the base of this half pipe. Well, what did we say is true of that? We said x2 had to be equal to 1. x1 could be anything. Why don't we just call it t? So t can be any real number. So our global minimizers is going to be the set of all points t and 1 in the x1, x2 plane, where t can be any real number. This is a parametrization of this line that runs along the base of the half pipe. And if you were thinking in terms of parametric equations, so maybe when you took your multivariable calculus course, how would you write this line? Well, you would say, okay, x1 is t, x2 is equal to 2. What's our z? Well, remember, if you plug t in for x1 and 2 in for x2 here, you get 0. And so this would be our set of parametric equations that would characterize that in 3D. Again, the way that you might have seen it in your introductory multivariable calculus course. Thinking in our terminology about minimizers, we should also note that these are not strong local minimizers. They are weak local minimizers. because this objective function has this flat spot at the bottom. Finally, our last topic is going to be that of the isolated local minimizer. So a point x star in Rn is an isolated local minimizer of f. If there exists a neighborhood n of x such that it's the only local minimizer in that neighborhood. So think of the picture. Can you find, and think of it like, can you zoom in enough where you get your function to have some neighborhood where your x star is the only one. There's no other local minimizer inside this neighborhood. So then we have to ask a couple questions. If you have an isolated local minimizer, does it have to be a strict local minimizer? So think about that for a minute. Can you have a flat spot? Well, the answer is no. Because if you had a flat spot, then it would have immediately adjacent to x star another local minimizer. That wouldn't work. You're not going to be able to zoom in and find a neighborhood where x star is by itself as a local minimizer. So it is true. Any isolated local minimizer is also a strict local minimizer. What about the other way? Are all strict local minimizers isolated? So if you have a strict local minimizer, does it have to be the case that you can find a neighborhood where it's the only one? And the answer to that is no, because you can cook up some of these cool examples where you have a global minimum, like in this case, but it is not isolated. And so, you can do cool things when you feed 1 over x to your trig functions like cosine or sine. So we have x to the fourth times cosine 1 over x plus 2x to the fourth if x is non-zero. And then it's 0 when x is equal to 0. So first, forget about the cosine 1 over x term here. Essentially, as x is approaching 0, you're going to knock out these two terms. The 2x to the fourth goes to 0. And then, of course, x to the fourth times cosine 1 over x, that's a competition between the two, but the x to the fourth going to 0 will win. So this function, as x approaches 0, does in fact approach 0. And so this fills in the hole. Now, if we graph it in your typical scale, this is what it looks like. So notice the x and y axes here. So the x-axis goes from about -4 to 4, and the y-axis from -5 to 15. And you look at this thing and realize, okay, we expect if there is a global minimizer, it's right there at the origin. The lowest point this thing can achieve is a y value of 0. Well, what if we change the axes a little bit? We zoom in just the right way. And so notice how much the axes have changed here. So down on the x-axis, we're going from about -0.15 to 0.15, but on the y-axis, we're on the scale of 1 over 10,000. But you see that you have this wiggly behavior. And so in this picture, is x equals 0 an isolated local minimizer? Well, it's not in this picture. If we tried to pick this -0.1, say, to 0.1 as our neighborhood, we couldn't say that x equals 0 is the only local minimizer in there. Well, what will happen is if you try to zoom in, so now we look in Desmos. Let's zoom in. That neighborhood's not going to work either because you have all these other local minimizers in here. What if we try and zoom in again? We can keep doing it, and we will always have the presence of these other local minimizers in any interval containing x equals 0. And so because of that, it's not isolated. It is the global minimizer of this function, but you can never find a neighborhood where it's by itself without other local minima. So that's kind of an esoteric example, but this is kind of the idea of the case where you can have a global minimizer, or even say which is also a local minimizer, but it is not isolated. This discussion is meant to make us fluent in the language of minimizers for nonlinear optimization. And so we'll explore where we can go with this in future lectures.